Good morning, everybody. Today we shall see about we shall discuss about the BJT small signal analysis. In the last class, we discussed about modeling of a transistor as far as the alternating signals are concerned. So that too when small signal and low frequency response of a transistor is of interest to us. Now today we shall see when the transistor is used in an amplifier circuit which includes the biasing arrangement. So how much of voltage gain does it give, and how much of input impedance it offers, and how much of output impedance it offers, and what is the current gain, and so on. Please look at this circuit. So this circuit is a typical fixed bias circuit with voltage divider bias to the base side, and the configuration is common emitter configuration. And you have the input signal applied through this coupling capacitor, and the output signal is tapped through this coupling capacitor, output side coupling capacitor. Now we shall determine the voltage gain, current gain, input impedance and output impedance of this amplifier circuit given the transistor model. So that is the problem now, and let us analyze it. Now please note that the analysis boils down to the application of Kirchhoff's voltage and current laws once you replace the transistor by its circuit model. Since you are going to replace it with the circuit model, or when you replace the transistor by a circuit model, it becomes a simple network to be analyzed in terms of output voltage and input voltage and output current and input current and so on. It is a simple circuit analysis problem once you replace the transistor by its model. Well, as far as the coupling capacitors are concerned, at mid-band frequencies, the impedance offered by the coupling capacitors is negligibly small, therefore we can replace them by a short circuit. For alternating signals, this can be replaced by a short circuit. So this is one change, one simplification which we can bring in. And the supply, please note that the supply is a DC supply, and a DC supply means it can only have a DC voltage of VCC volts. When some current is passed through it, and the current has say DC component and some alternating component, so this alternating component does not create any additional DC voltage across it. So I repeat, when you pass a current through it, a DC current and an alternating component through this supply, it doesn't offer any other alternating supply voltage. So you will find that the voltage drop is VCC volts in spite of an alternating current component passing through it. Hence, as far as the alternating component is concerned, it is like a short circuit. So when you do the circuit analysis for alternating components, the supply can be replaced by a short circuit. Now let us do this, let us bring in these two into the circuit analysis, and by bringing these two into the circuit analysis, that is replacing the coupling capacitor by a short circuit and replacing the supply by a short circuit and introducing the model of the transistor here, we can get the equivalent circuit. So equivalent circuit of this circuit is as follows, as shown here. So we have here, this is the input, and we have R2 to the ground, and R1 is also shorted to the ground because we replaced VCC by a short circuit. Therefore, R2 is also coming in parallel with R2. R1 is also coming in parallel with R2. And here you have a resistance between base to emitter in the transistor model. So this is beta Re, and we have here a current dependent current source between the collector and the emitter here, and this is 1 plus beta, beta times IB, where IB is the current flowing into the base, IB, and you have RC between the collector point and the ground point. And the output voltage is tapped now across the RC effectively. This is the equivalent circuit. Now, with this as the base current, since this is the base current flowing into the base, so the current, output current is beta times IB, and this output current is drawn from RC. If you treat RC as your load itself, then the load current is going to be minus IC, and that is minus beta IB. You can treat this as the load current if RC is the load. So it is possible that we in certain applications we connect the load resistance over here in place of RC, or it is also possible that we connect we use an RC for biasing purposes and connect an external load resistance here. So you can do either way depending on the application. Now, for the time being, considering RC as the load, the collector current itself with opposite sign becomes the load current. And in determining the current gain, you can treat this as the output current and this as the input current over here, and that the ratio gives you the current gain. Now let us analyze the circuit and find out the voltage gain, input impedance, output impedance, and so on. Please note that here this is the equivalent circuit of the transistor. This is the approximate equivalent circuit of the transistor using the RE model. And if you want to improve the accuracy, you have to introduce the output resistance of the transistor R0 over here. Well, when RC is much smaller than R0, we can neglect the effect of R0. Otherwise, for a more accurate analysis, R0 has to be introduced here. Any questions on the equivalent circuit of this particular amplifier circuit? Any questions? Okay, if there are no questions, let us proceed further. Now let me solve this circuit. To simplify the circuit over here, so let us replace R1 and R2 by a single resistance R, which is equal to R1 in parallel with R2, and this is beta Re. Now, if the input voltage Vi is applied here, then the current IB is equivalent to IB is Vi divided by beta Re.
Could you write a little bigger?
Sure. Then the output current IC is known to be beta IB. Therefore, IC is equal to beta IB is equal to Vi by Re itself. Now, IC is expressed in terms of the input voltage Vi. Now, output voltage V0 is, so this IC flows through RC, this is RC, therefore output voltage V0 is minus IC into RC, because the current direction is in the opposite direction to RC, in the opposite direction to this V0. Therefore, the voltage gain AV is equal to V0 by Vi is equal to, by substituting this over here, so you will find this as minus RC by Re. This is the expression for the voltage gain, minus RC by Re. As an example, if RC is 5 kilo ohms and if Re is about 10 ohms, so you will get an voltage amplification of 500, minus 500. You will get a negative sign here, because when you apply a signal of this type, so say it has the first half cycle is positive going and the next half cycle is negative going in a sinusoidal signal, then the output voltage you get here is like this, the waveform is like this. So you will get a negative half cycle first and the positive half cycle later. That means this is going to be multiplied by some negative gain. So that's why the positive half cycle becomes a negative half cycle and vice versa. What is the reason? When the voltage increases here, base current increases, and as a result collector current increases. When collector current in this direction increases, the voltage at the collector decreases, it drops. Therefore, when the rise is like this, so the output voltage falls like this. So that's because the current direction is in this direction, and that current is proportional to the input current, and input current is proportional to the input voltage. So because of this reason, the voltage gain is negative. Now, what is the input impedance of this circuit? This is the voltage gain, therefore. Now, input impedance. Now, look at the circuit. The input impedance is given by, as we have defined earlier, is given by VI by II, that means the input voltage, the voltage applied across the input terminals, so divided by the current, so that is drawn by the circuit from the supply. And please note that this voltage and the current are related by this resistance. Therefore, the input resistance is going to be so this resistance R in parallel with beta Re. That means it is R1 in parallel with R2 in parallel with beta Re. Hence, the input impedance is R in parallel with beta Re, so which is equal to R into beta Re by R plus beta Re, where R itself is the parallel combination of R1 and R2, therefore it is R1 R2 by R1 plus R2. As an example, if R1 is 10K and R2 is 1K, and say beta Re is also 1K, Ri is 10K in parallel with 1K in parallel with 1K. It is approximately 10 by 22. It is approximately 500 ohms or 470 ohms. So that is the order of the input impedance. Whereas the transistor has an input impedance of the order of 1 kilo ohm, and because of R1 and R2, the parallel combination coming across it, the input impedance further drops. So what is the effect of the biasing resistances? The biasing resistances drop the input impedance of the transistor further. And what is desirable? Do we prefer a large input impedance or small input impedance? For voltage gain, we expect large input impedance so that this circuit doesn't load the supply. This circuit or the amplifier doesn't load the supply. Now let us discuss about the output impedance. So bringing in the same equivalent circuit, so this is the output side. Now what is the impedance looking into the terminals when the input is replaced by a short circuit? How do we define the output impedance? If you connect a supply here and replace the input by a short circuit, how much current is drawn from the circuit is measured, and the voltage divided by that current that flows inside is the output impedance. Or when the input is replaced by a short circuit, the impedance looking into these terminals is the output impedance. And now when the input is replaced by the short circuit, there is no driving voltage here, therefore IB is 0, hence this current is 0. Current is 0 means it is an open circuit, and the impedance looking into these terminals is now RC. Hence the output impedance in this circuit is RC. Is equal to RC itself. Now current gain. Current gain is defined as the output current or the load current divided by the input current. If I express it as the load, IL divided by II is the current gain, and IL is minus IC, that is minus beta IB, and divided by the II. Now II can be expressed in terms of looking at the equivalent circuit here. II and IB are related. So how are they related? II, in fact the II gets shared between this resistance and this resistance, and the net result is IB. IB is II into R divided by R plus beta RE. Therefore we can express IB in terms of II. IB is II into R divided by R plus RE into beta. So this is the ratio. Now if you substitute for IB here, so you will get the current gain as, if you substitute this expression in this, you will get the current gain as minus beta into R by R plus beta RE. So this is the expression for the current gain. And in some books we follow the notation as the output current. We follow some notation where the output current is defined as the current going into the node. If you follow that notation, wherein the current going inside as the output current, so then the expression for the current gain would be I naught by II, that's equal to minus IL by II, that's equal to plus beta IB by II, and in which case the current gain is beta R by R plus beta RE. The difference is whether you consider the load current as the output current or the nodal current as the output current. If you consider the nodal current and the incoming current as the symbol for the output current, then the current gain is positive. If you consider the load current or the current going into the load as the output current, you will get the output, the current gain as a negative current gain. That is the difference. It only depends on the notation which you follow. So you can stick to any one of the notations and carry out your analysis. Any questions so far on the small signal analysis? It's a simple circuit analysis problem. Once you get the equivalent circuit. And how do you get the equivalent circuit? By replacing the coupling capacitances by short circuits and by replacing the transistor by its model and replacing the supply, DC supply, by short circuits.
So why is this model not valid for large?
So the question, there is a question there. The question is, why is this model not applicable for large signals? Please note that while obtaining the model, we considered small signals and we considered the characteristics as a linear characteristics around the operating point. We determined the slope there and then used that as the resistance or inverse of the resistance. And so that therefore this model is strictly applicable for small signals, because we have linearized the characteristics, and the linearization of the characteristics is valid only for small signals. Hence it is applicable for, hence it is a small signal model and it is applicable for small signals. Well, you can also use it for large signals, but that is an approximation. That becomes only an approximate analysis. Any other question?
while calculating the output impedance, when we have the output impedance of the transistor also, then both of the RC and output impedance will become in parallel?
Well, the question is whether if you have an external load resistance RL, does RL also come into picture in determining the output impedance? Now, if the amplifier circuit is this, if this is the amplifier circuit and you are going to connect an external load resistance here and independent of the load, so this is the amplifier circuit, in which case the amplifier only involves RC, only involves RC. Therefore, the output impedance is RC itself. And when you connect RL, using the amplifier model, we can determine how much of voltage gain you can get. In using that, you will be using only this R0 and an external RL. Therefore, it doesn't include RL in calculating the analysis, doesn't include RL in calculating the output impedance. Now, if you treat RC itself as a load resistance, and if you want to determine the effect of the load on the transistor amplifier, then RC is also external to it. And the output impedance over here is infinity. Approximately output impedance is infinity. Therefore, when you introduce RC as load resistance, there is no further voltage drop here because of loading. Okay. So, in which case, please note that RC is external to the circuit when you treat RC as the load resistance. Any other question? Now, let us repeat this analysis with a more accurate model, that is by introducing the output impedance R0, which is of the order of 40 kilo ohms in the case of a common emitter model. Now, let us introduce R0 here. By introducing R0, are you expecting any change in Ri here? Ri still remains as the parallel combination of this resistance and this resistance. Therefore, Ri is R in parallel with beta Re, R in parallel with beta Re, and which is of the order of a few hundreds of ohms. Say a few hundreds of ohms to a 1 kilo ohm, which is of that order. Now, what about the output voltage? Earlier in the approximate model, we considered that the load current is equal to the output current. So that means the output current is considered to be flowing through the load RC alone. Now, this load current will be flowing through the parallel combination of R0 and RC. Therefore, output voltage is this beta IB minus beta IB into the parallel combination of R0 and RC. Hence, in the expression over here, for the output voltage, in the expression over here in the output voltage, V0 is, instead of minus IC RC, it is minus IC RC in parallel with R0. So now by substituting for this resistance, parallel combination resistance, in place of RC, you will get the voltage gain as minus RC in parallel with R0 divided by RE. That means the loading is not only by RC, the loading is also by R0, and the parallel combination is always less than RC. Therefore, we can expect some fall in the voltage gain in the accurate analysis. And What is it quantitatively? It is by the parallel combination of RC and R0 in place of RC alone. Hence, the expression for voltage gain is this in the accurate model. Now, what about the output impedance R0? R0 is now the output impedance RC in parallel with the small R0. So, this is the output impedance. This 40K comes in parallel with RC, and that is the output impedance. Both of them put together become the output impedance. And when you treat RC as the load, the output impedance is R0. It's not infinity, but R0. Now, let us determine the current gain. Now, there is a difference here. So, earlier the current gain, the output current is considered to be beta IB itself. Now, the output current is this I0, assuming the ingoing current as the output current, that means the nodal current at this node as the output current I0. So, this I0 is a fraction of beta IB now, because beta IB gets divided between R0 and RC. This beta IB gets divided between R0 and RC, and the part of the current that flows through RC makes our I0. Therefore, this I0 is this beta IB multiplied by R0 divided by R0 plus RC. Hence, in this analysis, this I0 is beta IB into R0 by R0 plus RC. This is I0, and when you divide it with II, because you have to divide this by II, and you can make this substitution over here, and as a result you will find the current gain as beta into R by R plus beta RE, that is input side current division, expression for input side current division, and here you have an expression for the output side current division. So, let me explain this once again. When these two resistances are absent, the current gain of the amplifier circuit is equivalent to that of the transistor, that is beta itself, when these two are absent. When this is introduced, there is a division in the current gain, in the current on the input side, because of which we got this expression R by R plus beta RE. Now, because of this R0, introduction of R0, we have another division of this current through R0 and RC. So, because of this division, we have an additional term coming into picture, so that is R0 by R0 plus RC. Hence, the current gain of the amplifier circuit is equivalent to the current gain of the transistor multiplied by the input side fraction and output side fraction, which are generated by the current division on the input and output sides respectively. Is clear? Now, what is the typical expression here? When R is much larger, before that, let us find an approximate expression here. When R is much larger than beta RE, that means when this is much larger than this, we can neglect this current that is part of the current that flows through this, and we can assume that the input current is equivalent to the current through the transistor itself. Similarly, when RC is much smaller than R0, we can treat the output current as the total current itself as the output current, in which case the gain is beta itself. That means when R is much larger than beta Re, this is almost 1 input side ratio, and when R0 is much larger than RC, this is also 1, therefore the current gain is beta. This analysis is for this kind of circuit, which is a fixed bias circuit with voltage divider bias on the input side. We have another important circuit, that is the self bias circuit, where we have an emitter resistance over here, and the emitter resistance that is incorporated provides you a very good advantage as far as stability of the biasing is concerned. Now, when you use a self bias circuit, what is the voltage gain, what is the current gain, input impedance and output impedance, what are the input and output impedances you get? That is of interest to us. Therefore, let us now analyze the self bias circuit, an amplifier with self bias circuit. Amplifier with emitter bias or with self bias. So let me give you the circuit. The circuit of the amplifier is like this. I am not showing the coupling. Okay, let me show the coupling capacitors, because I am calling it as an amplifier circuit. This is the amplifier circuit with self bias. The typical circuit which we use for amplification involves a bypass capacitance here. So let us first analyze the circuit without the capacitance, and then I'll explain about why this capacitance is required. So for the time being, you treat that the capacitor is not there. Now let us get the equivalent circuit of the amplifier. Please note that the emitter is now not connected to ground. Emitter is connected through a resistance to ground, and between base and the ground you have these two resistances R1 and R2 coming into picture. Once you replace VCC by a short circuit, R1 and R2 comes in parallel between the base and ground, and between the ground and the emitter you have this resistance. Other than that, the equivalent circuit is similar to what we have got earlier. So let me draw the equivalent circuit of the amplifier. It is the small signal AC equivalent circuit. So between the input and ground we have R1 in parallel with R2, and between the base and emitter we have beta Re as the resistance, and we have the current dependent current source beta IB, where IB is the base current, and between this emitter and the ground we have this RE, and all these are grounded. And this is the collector point, this is the base, this is the collector point. Between the collector point and the ground, or VCC to ground, we have RC. Now this is the output voltage. Where this is the input voltage and this is the input current, and in the convention which we are following, so this is the output current. This is the equivalent circuit of the amplifier circuit shown here. Please note that the supply is here. And the supply is a short circuit for alternating signals. Hence, this RC, one end of RC is connected to the collector and the other end is connected to the ground. And emitter, similarly base is connected to the ground through R2 and R1, and emitter is connected to the ground through RE. Hence, this is the equivalent circuit. And between base, collector and emitter, we have the transistor equivalent circuit. Now, IB flows through this resistance, beta IB flows through this source, and therefore the current flowing through RE is equal to IB plus beta IB, that is 1 plus beta into IB. Now let us write down the equation, the Kirchhoff's voltage law equation in this loop. So that will give us VI as equivalent to beta RE plus 1 plus beta into RE whole into IB. So this voltage drop is equal to voltage drop across beta RE, that is beta RE into IB, beta RE into IB, plus the voltage drop across this resistance, and that is 1 plus beta into IB into RE. Hence, the impedance, input impedance between this point and this point, input impedance is this voltage divided by IB. So here, if you treat this as the input impedance Ri dash is equal to Vi divided by IB, and that is equal to beta Re plus 1 plus beta into Re. Therefore, introducing Re here is like introducing Re into 1 plus beta as a resistance in series with this. When Re was not there, the input impedance was beta Re here, and here it is R1 in parallel with R2 in parallel with beta Re. So here it was only beta Re. Now by introducing Re, what's happening? The input impedance is becoming beta Re plus 1 plus beta into capital E. So that's why the input impedance, an expression for the input impedance here is like this. Now the input impedance of the amplifier, the total amplifier, that is Ri, can now be obtained as the parallel combination of the impedance over here and R1 in parallel with R2. Therefore, the input impedance is R1 in parallel with R2 in parallel with Ri dash, that is beta Re plus 1 plus beta into Re. So this is the expression for the input impedance. So I have given it in a short manner. Please note that once you have the resistance equivalent here, you can find out the current division, and then Vi by Ii can be determined in terms of Vi by Ib, and you can arrive at this expression. Now what's happening to the input impedance by introducing Re related to the earlier circuit? The input impedance is increasing by 1 plus beta times Re as an additional term coming in series with beta Re. Therefore, input impedance is considerably increased in this circuit, provided R1 in parallel with R2 is much larger than this. If this itself is say 1K and this is 1 mega ohm or 100 kilo ohms, so the parallel combination is going to be 1K itself, and because this is negligible compared to this. But if this is 100K and previously beta Re is 1K, the parallel combination would have given you approximately 1K. Now with this as 100K, and if this becomes 100K, the parallel combination will give you 50K. Therefore, this increase in the resistance is effective only when R1 and R2 parallel combination is very large compared to beta Re. So there is a significant change in the voltage gain also, and we shall discuss about it in tomorrow's class. Any questions?